Welcome to The Explainer, where today we're pulling back the curtain on a really powerful and frankly kind of surprising idea at the very heart of how science actually works. So let me ask you a question. How does science get to the truth? I think most of us, we imagine it's all about proving theories, right? Just stacking up more and more evidence to confirm an idea. But what if I told you the real secret, the actual engine of discovery, is the exact opposite? What if it's all about trying to prove our best ideas wrong? Okay, let's dive into this. The way we usually think about it is called verification. You go out and look for proof that you're right. But the philosopher Karl Popper came along with a much more powerful idea: falsification. The goal isn't to confirm your theory, but to hunt for that one single piece of evidence that proves your theory is completely false. Just think about it, right? You can see a million white swans, and it doesn't definitively prove that all swans are white. But finding just one black swan, boom, the theory is instantly shattered. Now, probably the best way to wrap your head around this whole process is to think like a detective solving a case. We're going to walk through this deductive method, and it's got 4 key steps. First, you got your theory. That's your main suspect. Next, you deduce a specific prediction from their story. That's the key clue. Then, you run the test. That's the actual investigation. And finally, you draw your conclusion, the verdict. So let's start with step 1, the suspect, or in our world, the theory. And listen, not just any old theory will do. A good scientific theory, a good suspect, has to tell a story that we can actually test. It needs to be breakable. But before our detective even starts the legwork, the theory has to pass a few background checks. First up, is it internally consistent? Does it even make sense on its own, or does it contradict itself? Second, and this is the big one, is it actually scientific? This means it must be falsifiable. You have to be able to imagine some kind of observation that could prove it wrong. If you can't, it's not really science, it's more like a belief. And finally, if this theory survives all the tests, is it actually an improvement? Does it push our knowledge forward? All right, so we've got a solid, breakable theory. Our suspect's story is holding up so far. Now it's time for step 2, the deduction. This is where we zoom in from that big general story to a single specific clue we can actually go out and look for. You see, our theory usually starts out as what's called a universal law. It's just a fancy term for a big, broad statement that claims to be true everywhere all the time. Let's use a super simple example. Whenever a thread is loaded with a weight exceeding its tensile strength, it will break. Make sense? Seems pretty obvious, right? But here's the thing. You can't really test a vague, general idea like that on its own. You've got to get specific. So we add what are called initial conditions to set up a very particular test. So let's say condition 1 is, this specific thread right here has a tensile strength of exactly 1 pound. And condition 2, the weight we're about to hang from it, is 2 pounds. And this is where the magic happens. You combine that big universal law with those super specific initial conditions, and you can deduce a single, concrete, totally testable prediction. It's not a fuzzy idea anymore, it's an undeniable consequence. In this case, the prediction is simple. This thread will break. All right, now for the fun part, step 3, the investigation. This is the experiment. This is where the detective gets their hands dirty. And you have to remember the goal here. We are not trying to be gentle with our theory. We are making a systematic, rigorous, and even a ruthless attempt to make it fail. We are actively trying to break this thing. And you can't just run any old experiment. There are strict rules for what counts as good evidence. It can't be a one-time fluke. The experiment has to be repeatable. The results have to be intersubjectively testable, which is just a fancy way of saying that anybody, anywhere who follows the exact same recipe should get the exact same result. The evidence has to be objective, has to be reproducible, no exceptions. Okay, the lab coats are off. The investigation is over. We have the results. It is time for the final step, the moment of truth, the verdict. This is where we take what we predicted would happen and put it side by side with the cold, hard facts of what actually happened. And the logic here is it's so powerful, it's ironclad. Check it out. If our theory is correct, then our prediction has to come true. But what if our experiment shows the prediction is false? What if the thread didn't break? Well, therefore, our original theory has to be wrong. It's a chain reaction. The failed prediction reaches all the way back and demolishes the theory it came from. So this is the whole game right here. It all comes down to two possible verdicts, and only two. On the one hand, if your prediction was false, the thread didn't break, then the theory is falsified. It's done, rejected. The verdict is final. But what if the prediction was true? What if the thread did break? Well, we don't say the theory is proven. No. We say it's been corroborated. All that means is it survived this test. It proved its toughness. For now, it just lives to face an even harder test another day. And that right there, that's the real engine of scientific progress. It's not about collecting a bunch of facts we think are right. It's about the failures. It's the experimental falsifications that force us, that compel us to throw out the bad ideas and go searching for better, stronger, more accurate theories about how the world actually works. So if you take one thing away from all of this, let it be this powerful idea. Science isn't really about proving what's right. It's about systematically eliminating what is wrong. Reliable knowledge isn't some big library of proven facts. It's more like a collection of survivors. It's the set of ideas that has withstood the most ruthless, rigorous attempts to tear it down. True knowledge is simply what's left standing after the battle. And that leaves me with one final thought for you. This whole method, it isn't just for scientists in white coats. It's a powerful tool for thinking for all of us. So think about it. What's an everyday idea or a long-held belief that you have that you could put to the test? Not by looking for reasons you're right, but by actively searching for that one single piece of evidence that could prove you wrong.